Hello everyone, welcome to, I guess this might be our third video in 3.2. So last time we talked about what happens at the ends of a polynomial. Today what we want to talk about is what's going on in the middle. So how are we going to do this? How are we going to figure out what's going on in the middle? Well, just kind of draw something really quick. So let's say we figure out what the end behavior is, something like this. Just pretend it's something like this. Now, what's going to happen is the polynomial is going to wiggle in here. Maybe I'll do it in a different color. I don't know what it's going to look like. Maybe it's going to look something like this. So how am I going to figure out what's going in the middle here? What I'm going to take advantage of, or what I'm going to try to look for to figure out what's going on in the middle, is I'm going to try to figure out where the x-intercepts of a graph are. If I can figure out where the x-intercepts are, I can figure out what's going to happen in the middle. So here, let's give a kind of a few names that we have for these here. So I know you may know them as x-intercepts, but there's other words we use. Sometimes these are called the x-intercepts of a graph. You might sometimes hear the textbook call these the zeros of a graph, well, because that's where the output of the function is 0. You might also hear some textbooks call these the roots of a polynomial. Why roots? My guess is this looks kind of like, I don't know, the roots of a tree. And so they call them the roots. X-intercepts, zeros, roots, it all means the same thing to me. Okay, so let's do some examples of graphing and graphing a whole polynomial, putting all the pieces together. Okay, so here's our example. Let's actually erase them this way, a little bit more room. So our first example. Okay, so let's say we have the function p of x, which is equal to x cubed plus 2x squared minus 8x. So what we're going to do here is we're first going to find the roots, or the x-intercepts, or the zeros. So what I want to look for are what values of x give me an output of 0. So this is how I'm going to find the roots. So how we're going to find the x-intercepts, how are we going to solve an equation like this? We're always going to factor. So let's go ahead and try to factor this. So the first thing you should always check for when factoring is to see if there is a common factor for us to pull out. Notice that each of these terms have a common factor of x. So let's factor out an x, and we'll be left with x squared plus 2x minus 8. So we can continue on here. What we want to do is now we want to factor this quadratic. So 0 equal to x. This quadratic right here, maybe a blue, this is going to factor something like this. So remember how to factor quadratics is what we want to look for is we want to look for the factors of the constant term that add to the middle coefficient. So what are the factors of negative 8 that add to 2 here? Let's think about it. The factors of negative 8 that add to 2, it's got to be some sort of combination of 4 and 2. Okay, well, they have to add to give me positive 2, so the bigger number has to be positive, and this one here has to be negative. So now let's figure out what the zeros are. So what I love about factoring is this form is screaming at us the x-intercepts. Notice that if I were to plug in the x equals 0, I'm going to get 0 times this, 0 times anything is 0. So one of the solutions is x equals 0. Different color. One of the solutions is x equals 0. Another solution here is, notice If x was -4, I'd get -4 plus 4. This piece would zero out, which would zero everything out. So another solution would be x equals -4. And our last zero here. What value will make this zero? Well, if I plug in 2, 2 minus 2 is 0, that'll zero everything out. So x equals 2. So these are the x-intercepts. These are the roots of the quadratic, or the roots of the polynomial. So now let's sketch this. So we have our roots. So our roots are x equals 0, x equals -4, and x equals 2. Okay. What I want to do here is let's leave the factored form of this polynomial up. So p of x is the same thing as x times x plus 4 times x minus 2. So we factored it. So this is what we know about the graph. What we know about the graph is we know that the graph has to hit these x values. So I know the graph is going to cross, or it's going to hit the x-axis at 0. It's going to hit the x-axis at -4. And it's also going to hit the x-axis at 2. So that's what I know so far. What I also know is I know the end behavior of this function. The leading term on this polynomial is x cubed. It'll have the same end behavior as x cubed. So its end behavior will look just like a cubic. Okay, so now we just have to figure out what's going to happen here. So there's two things that can happen. I know the function is negative over here. Now the only way the outputs can flip from being negative to positive is by crossing through the x-axis. I have to cross through 0 to be able to flip sign. So what I want to know here is, as I'm going up, does the graph cross through the x-axis or does it bounce? That's what we want to know here. And how are we going to figure this out? One of the best tools we can use, and this is a tool that I use all the time, not just in pre-calc, in calculus, in all sorts of math classes, making a sign chart. So what we're going to do is we're going to make what's called a sign chart. So what I want to just draw here is the x-axis. So this here is the x-axis, and this is p of x, which we're trying to graph. So I'm going to write down my zeros. So I have 0 is a 0 or a root or an x-intercept, all mean the same. 2 and -4. So what I know is that the graph can only flip from being positive or negative by crossing through these values. So the thing I know already right off the bat is that the end behavior of this function is negative. It's going towards negative. So I already know when I plug in any value less than -4, the outputs are going to be negative, so I'll put a bunch of negative signs here. Another way to verify this is let's just pick any number less than -4. How about we choose in a different color, maybe blue. What if we choose, now it doesn't have to be -5, negative, how about like -100? So what if I plug in -100 into this function? What am I going to get as an output? Okay. Well, if I plug in -100, let's actually write this right here so we can keep track of it. We have the x times x plus 4 times x minus 2. Well, if I plug in -100 into x, well, that's going to be a negative value. If I plug in -100 in for x here, -100 plus 4, that's still a negative value. If I plug in -100 in here for x, -100 minus 2 is still a negative number. So when I plug in -100, I get a negative times a negative times a negative, which has a net value of negative. So when I plug in -100, I'm going to get output value of negative. Let's figure out what happens in between -4 and 0. So I know the graph is negative, but as it comes up, does it bounce? Does it stay negative, or does it cross through and turn positive? Well, let's see. Okay, so let's plug in any value between 0 and -4. How about our test point is, how about -1? So if I plug in -1 for x, well, that's a negative value. -1 plus 4 is a positive value. And -1 minus 2 is a negative value. So I have a negative times a positive times a negative. I have an even number of negatives, so this will be positive. So I know the graph now becomes positive. So what the graph must do, if I'm piecing this together, is the graph is negative, and then what's going to happen is the graph is going to cross through this x to the fourth. Or this is x, the function is going to cross through the root -4. Okay, well, so now what happens here at 0? Or what happens between 0 and 2? So I know the graph is going to hit right here, but is it going to bounce or is it going to go through? Well, let's pick a point. How about x equal 1? Any number between 0 and 2. So if I plug in x, if I plug in 1 for x, well, it's a positive number. If I plug in 1 for x here, 1 plus 4 is a positive number. If I plug in 1 here, 1 minus 2 is a negative number. So a positive times a negative, the net result will be a negative. So when I plug in any value between 0 and 2, the output is going to be negative. I don't care exactly what the output is, I just care whether it's positive or negative. And what I know is that it's negative. So the graph is going to go ahead and cross through. So you might already think what it has to do at 2. It has to match up with the end behavior, so it has to cross through. There's no other option. If it bounced, it would go down to -infinity, but we know it goes towards positive infinity. So I know it has to cross through, but let's just check it. Let's plug in any value bigger than 2. I don't know. Could be 3. How about 100? Could be 1,000. Any number bigger than 2. If I plug in 100 for x, that's a positive value. If I plug in 100 for x here, 100 plus 4, that's a positive value. 100 take away 2 is another positive value. A positive times a positive times a positive is a positive. So what's going to happen is the graph is going to become positive. So the graph has come up and connect. So here is a graph of this polynomial. Let's do another example. Whew. Okay. So our next example, let's say p of x is equal to x to the fourth minus 4x cubed plus 3x squared. So the first thing I'm going to do here is I'm going to go ahead and find the roots. So I want to know when the outputs of the function are 0. Again, I didn't say this, but go ahead and pause the video and try this on your own first. Okay. So the first thing I'm going to do is I want to try to factor this. I want to know when the output of this is 0. And so when I look at these three terms here, I should recognize that they have a common factor of x squared in them. So let's go ahead and factor out an x squared. And what I'm going to be left with in the parentheses is an x squared minus 4x plus 3. Let's continue factoring. So I'll get x squared. Now I just need to factor this quadratic. So I need factors of 3 that add to -4. Well, since this is negative, I think I need both these numbers to be negative. It has to be a 1 and a 3 since 3 is prime, and they both need to be negative. So a -1 and a -3 give me a positive 3. -1 plus -3 is a -4. So now that we have this factored, let's look for the roots. In this case here, what values of x can I plug in to get an output of 0? Well, notice if x is 0, 0 squared will be 0, that'll 0 everything out. So this piece here is screaming at me. that x equals 0 is a solution. This factor right here is yelling at me. It's screaming. It's saying x equals 1 is a root. And this term right here, it's yelling. Maybe put, I don't know, don't put earplugs in. We want to hear it. X equals 3 is a root. So here are the roots. My computer died. Hold on. Didn't die. I just went to screen. Okay, perfect. So these are the roots. Okay, so let's write those down. Roots. We have x equals 0. We have x equals 1. We have x equals 3. Okay. So let's erase a little bit of this. Let's go ahead and keep the factored form of this polynomial up. What was that? It was x squared times what we had. I think it was x minus 1 and x minus 3. Okay, so let's graph this. Okay, what do we know? What do we know? First off, we know its end behavior. Its leading term is x to the 4th, so its end behavior will behave a lot like x to the 4th. So here's its end behavior. Okay. I know that it has to cross the x-axis at these values of x, so I'll go ahead and record those. So at x equals 0, at x equals 1, and at x equals 3. Okay, so now I just need to figure out when it hits these roots, does it cross through or does it bounce? We'll make a sign chart. Okay, so we have 0, 1, and 3. So based on the end behavior, we already know what's happening for values less than 0. They have to be positive. And we know what has to happen for values bigger than 3. They also have to be positive. And you could verify this just with some test points. Let's plug in a number less than 0. I don't know, any value less than 0. How about negative 10? So let's think about what happens here. And let's write x squared times x minus 1 times x minus 3 here. Well, if I plug in negative 10 into here, negative 10 squared is positive, so I'll get a positive value. Negative 10 minus 1 is a negative value. Negative 10 minus 3 is another negative value. I have a positive times a negative times a negative. 2 negatives make a positive, and that result here will be positive, which is agreeing with our end behavior. Okay, let's see what's happening between 0 and 1. Between 0 and 1, let's see, let's pick, I don't know, how about x equals, how about 0.5 or 1/2? Well, if I plug in 1/2 and I square it, it's going to be positive. Notice that no matter what value I plug in for x squared, the output will always be positive. If I plug in 1/2, 1/2 minus 1 is a negative number. 1/2 minus 3 is another negative number. So it's going to be positive here. Interesting. So what is the graph doing? It's staying positive. It's coming down to 0. And then what's happening is it's bouncing. So it's going to bounce off of 0. What's going to happen at 1? Let's see. Let's plug in any number between 1 and 3. How about x equals 2, for example? Okay, so x equals 2. Let's plug that in. So if I plug in 2 into x squared, 2 squared is still positive. 2 minus 1 is positive. 2 minus 3 is negative. So I have a positive and a positive and negative. The net result will be negative. So what's going to happen is the graph is going to cross through 1. Now from here we already know what has to happen. It has to connect with our end behavior. So it has to cross through 3. Well, let's just verify that. So again, we saw here that this was negative. So let's verify. Any number bigger than 3. How about, I don't know, 1013. Why not? So if I plug in 1013 and square it, that result will be positive. 1013 minus 1 is positive. 1013 minus 3 is also positive, so the net result will be positive. Whew, it agrees. It's a great way to check your work. It should match up with your end behavior. Okay, let's make a note of something that happened here. Notice that around 0 it bounced. And also notice that where we actually got the 0 root from was from the x squared piece. Notice that its power was 2. We would actually say that the root 0, since the factor that it came from has a power of 2 on it, we would say what's called the multiplicity. The multiplicity of the 0 is 2. So multiplicity. Let's write that a little bit better. Multiplicity. Okay, the multiplicity m is going to be 2. The multiplicity of x equals 1, it came from this factor. It has a 1 on this factor. It's to the power of 1, so its multiplicity will be 1. And for 3, its multiplicity will be 1 because the power here is 1. So what's neat here is we can oftentimes use multiplicity to understand whether a function bounces or crosses through. If it has a multiplicity that is even, it'll bounce through. Why? Well, let's think about it here for a second. When I'm around 0 here, if I plug in a value that's less than 0 and I square it, it's going to be positive. But when I cross over here, now when I plug in a number a little bit bigger than 0 and I square it, it's still going to stay positive. This is the only piece here that could possibly flip the sign of the function. And since it's being squared, it can't flip the sign. So that's why it's bouncing. Over here, since they have an odd multiplicity, when I'm on one side, it'll be, in this case, positive. But when I go to the other side, it's going to flip sign if I have an odd multiplicity. We'll see that with tons of examples. Keep that in your mind as we do more examples. Let's do another one. Okay, so as our next example, let's say we have x cubed plus a 3x squared minus a 9x minus 27. So let's go ahead and first try to find the roots of this polynomial. Okay, so let's try to figure out what values of x give me an output of 0. So when we're trying to factor something like this, it's a little bit tricky because I don't have a common factor in any of these 4 terms. So what we need to do is we need to think about another factoring technique, something that hopefully you remember, something that's called factoring by grouping. Whenever you have a polynomial that has 4 terms in it, what you should try to do is you should try to factor by grouping. How do we factor by grouping? Well, the first thing I'm going to do here is I'm going to get rid of these negatives by doing plus the opposite. So let's say this is plus -9 and plus -27. So let's try factoring by grouping and see if it works. So when you factor by grouping, you group the first 2 terms together and you group the second 2 terms together. And in each of these sets of parentheses, we're going to factor out the greatest common factor. So 0 is going to be equal to, well, what's the largest common factor? What's the greatest common factor in these 2 terms? I think it's x squared. So we can go ahead and factor out an x squared. So I'll get an x plus 3 plus, well, I think I can factor out, I have a common factor of -9. So let's factor out a -9. And I'll be left with, what? I'll be left with an x plus 3. Great news. Great news. Notice, I've now taken something that had 4 terms into it, and now it has 2 terms. And each of these terms has a common factor of x plus 3. So what are we going to do? we're going to factor the common factor of x plus 3 out front. So what are we going to get? We're going to get that 0 is going to be equal to, I'll write it in blue, I'll have the x plus 3 times, what am I going to be left with? The x squared minus 9. Or you could put plus negative 9 if you like. Awesome. So notice, if this is confusing you, if I took this x plus 3 and I distributed it back into the set of the parentheses, I'll get x plus 3 times x squared, bam. X plus 3 times negative 9, bam. Okay, beautiful. Factoring by grouping, love it. Okay, so let's see if we can factor this anymore. So 0 will be equal to x plus 3. I think we can factor this a little bit more. I hope you recognize this is a difference of squares pattern. So a difference of squares, you kind of forgot. If you have something of the form x squared minus b squared, that is always going to factor to x minus a times x minus a, sorry. If you have anything of the form a squared plus b squared, that's going to factor to a minus b times a plus b. So this is how we factor a difference of squares. So in this case here, think of this as a 3 squared, so this will factor to x minus 3 times x plus 3. Or if we want, we have two common factors of x plus 3. We could write this as 0 is equal to x plus 3 squared times x minus 3. So what are the zeros? Well, notice from this x plus 3 squared, if I were to plug in x equals negative 3, this whole piece would get zeroed out. Similarly over here, if I have x is equal to 3, this will zero everything out by plug in 3. So those are the roots. So we have the roots. The roots are x equals negative 3 and x equals 3. For fun, let's also talk about their multiplicity. Okay, so I got the negative 3 from this factor. This factor is being squared. It'll have a multiplicity of 2. So this is going to tell me it's actually going to bounce off negative 3. And we'll verify that with the sign chart. Now for this one, it has a multiplicity of 1. Think if there's a little hidden 1 right here. So it has a multiplicity of 1. Keep that in the back of my mind. Okay, let's graph this. So we have p of x. I'll leave it in its factored form. It's factored to a x plus 3 squared times an x minus 3. Let's talk about the end behavior. The end behavior will, you have the same end behavior as its leading term, which is x cubed. So its end behavior will look like this. And its roots are at negative 3 and at 3. So what I know here is since negative 3 has a multiplicity of 2, it's actually going to go ahead and bounce off of negative 3. And then since 3 has a multiplicity of 1, it's actually going to cross through. So let's actually verify that with the sign chart. So let's make our sign chart. So here we have our roots are at negative 3 and 3. Okay, so I already know, based on the end behavior, that it has to be negative over here because that's the end behavior. Over here, it has to be positive. Okay, so again, you could verify this. Let's say you plug in x equals negative 100. If I'm looking at the x plus 3 squared times the x minus 3, if I plug in negative 100, I'm going to get negative 100 plus 3. That's going to be a negative number, but I'm squaring it. That'll be positive. If I plug in negative 100 in here, negative 100 minus 3 is something that's negative. So the net result will be negative. So what's going to happen over here? So let's plug in a number between negative 3 and 3. How about x equals 0? It's a great number to plug in. Well, notice if I plug in 0 here, if I plug in 0, I'll get 0 plus 3, I'll get 3. I'll get 3 squared, that'll stay positive. But if I plug in 0 here, I'll get 0 minus 3, and that'll stay negative. Notice, because this is being squared, that this piece right here did not flip sign. And that's where that multiplicity comes in. It has an even multiplicity. It won't change sign when we flip over. So over here, it stays negative. And then we know it's going to have to cross through here to match up. So what's the graph going to do? It's going to come up here. It's going to cross here. Okay. So I know it has to cross through here. It's the only option. But let's just check it. Let's plug in a value bigger than 3. I don't know, 100. If I plug in 100 here, 100 plus 3, 103 squared, that's a positive number. 100 minus 3 is another positive number. It'll be positive. Awesome, degrees. So here. Also notice that it had a multiplicity of 1, and it's going to be crossing through. So this piece had a multiplicity of 1, so when I go from here to here, it's got a flip sign because I don't have this as an even power. The other thing that we should label in this graph is the y-intercept. That's the last thing we're going to label here. So how do I figure out the y-intercept? Well, that's the value of the function when I plug in 0. So let's figure out the y-intercept. If I plug in 0, let's look at this form of it. This will get zeroed out, that'll get zeroed out, that'll get zeroed out. I'll be left with negative 27, so I know it crosses the y-axis at negative 27. And there's the graph of the polynomial. Okay, let's do an example if we're trying to graph something that's already factored. Okay. So this will be our last example. Okay, so let's say I have p of x is equal to x to the 5th times x minus 2 cubed times 8x plus 3 squared. Okay, let's go ahead and graph this. They've already factored it for us, which is nice. So the first thing we want to do is let's go ahead and find its roots. So what will the roots be? Okay, so the roots, I want to know when the output of this function is 0. So I want to know when is this equal to 0. Well, if I plug in 0 for x, then that'll zero everything out. And this x equals 0 will have a multiplicity of 5. So m equals 5. I'll have another 0, another root of 2. If I plug in 2, that'll zero everything out. And it has a multiplicity of 3. Over here, let's say x is equal to negative 3. Negative 3 will have a multiplicity of 2. So there are our roots and there are its multiplicities. Okay. So what's great about multiplicity is what I know is since the multiplicity is odd here, the graph is actually going to cross through 0. Since this is an odd multiplicity, it'll actually cross through 2. Since this has an even multiplicity, it's actually going to bounce off negative 3. And we'll do that with the sign chart again just to verify. Okay, but here's the question. What is the end behavior? What degree is this polynomial? It's all factored. Well, let's think about it. So without doing all the work here, I have an x to the 5th. Now if I were to expand x minus 2 cubed, you have x minus 2 times x minus 2 times x minus 2. That'd be a lot of expanding you'd have to do, but you would have a you would have a x, let's erase this real quick. Let me just show you. So this is like an x minus 2 times an x minus 2 times an x minus 2. Here we have an x plus 3 times an x plus 3. So here I have an x to the 5th. If I were to expand this piece here, I would get some sort of x squared plus a bunch of stuff times another x minus 2. Here I'd have an x plus 3 times an x plus 3. I would have an x squared plus a bunch of stuff. Well, if I have an x squared times an x minus 2, that's going to give me an x to the 5th times something that has an x cubed in it, times something that has an x squared in it. But if I multiply these out, I'm going to have something that's like an x to the 5th plus, and then I'm multiplying it by another x to the 5th. So if I distribute that in, I'll have an x to the 5th times an x to the 5th. This has got to be an x to the 10th polynomial. Okay, so what I know here is this is a degree 10 polynomial. So another quick way to do that is you could just add up the exponents. 5 plus 3 is 8, plus 2 is 10. That's another quick way to figure out what the degree of this polynomial will be when it's in factored form, without having to expand everything. So again, we had our roots x equals 0, multiplicity of 5, x equals 2, multiplicity of 3, x equals negative 3, and a multiplicity of 2. Let's go ahead and graph this. Okay, so I have a root at x equals 0. I have a root at x equals 2. And I have a root at x equals negative 3. Okay. The end behavior of this will behave just like a x to the 10th, which is a lot like a parabola. Behave a lot like x squared. So I know that this has to be the end behavior. Okay, so let's take a look at what should happen. If I'm going to do this quickly, we can just look at the multiplicity. Okay, so as it's coming down here, what's it going to do around negative 3? Well, negative 3 has a multiplicity of 2. It's going to bounce. It's going to bounce. Okay. Now, what's it going to do about 0? Is it going to cross through 0 or bounce? It has an odd multiplicity. It's going to cross through. It's going to cross through. Okay. And how about at x equals 2? Well, it also has an odd multiplicity, so it's going to cross through at 2. So it's going to cross through, and it's going to come back up, and it's going to connect to our end behavior. So that's what the graph is going to roughly look like. Now, why did I kind of draw these little squigglies here? I'm going to be super picky about this, but it turns out that if I'm near 0 here, the graph will look a lot like an x to the 5th kind of piece. So locally, it'll kind of look like that squiggly, kind of like like the x cubed kind of piece, except it'd be like this. How about over here? For x equals 2. It's going to look a lot like something like an x cubed, so that's why it's a little bit squiggly here, and so on and so forth. Notice here around negative 3, it looks kind of like a parabola, like locally around negative 3. Okay. Now let's just verify this with a sign chart. But this is how you can do it really quickly. So with the sign chart, negative 3, 0, and 2, well, if I plug in a number smaller than negative 3, how about x equals negative 100? Negative 100 to the 5th power is a negative. Negative 100 minus 2 is a negative number. I'm taking that negative number and I'm cubing it so it'll stay negative. Negative 100 plus 3 is still a negative number. I'm going to get a negative number and I'm going to square that. That's going to be positive. So I get a negative, which is a positive, another positive. It's going to stay positive in here. Okay, let's say I plug in a number between negative 3 and 0. How about x equals, negative 1? If I plug in -1 here, -1 to the 5th power will still be negative. If I plug in -1 here, I'll get a -1 minus 2, that's -3 cubed, that'll be negative. And if I plug in -1 here, I'll get a -1 plus 3, which is a 2 squared, which will be positive. Notice that this piece did not flip sign, and that's because its multiplicity is even, so it'll still be positive. Okay, if I plug a number between 0 and 2, how about x equals 1? If I plug in 1, and I raise it to the 5th power, 1 to the 5th power is positive. 1 minus 2 is a negative number. A negative number cubed is negative. Sorry, I'm plugging in 1. Yeah, 1 minus 2 is negative, 1 cubed is negative. If I plug in 1 here, 1 plus 3 is 4. 4 squared, that's a positive number. Positive, positive, negative. That's going to be a net result of a negative. So it has to be negative in here, which is exactly what we have. Okay, something bigger than 2. Well, x equals 100. If I plug in 100 and I raise it to the 5th power, it'll stay positive. 100 minus 2 is positive. Cubed, that'll be positive. 100 plus 3 is positive. You square that, it'll be positive. So the net result here will be positive. So we can always use a sign chart, but what can make our lives a lot easier when we have it in a factored form is thinking about the end behavior, thinking about the zeros, thinking about their roots, and you can do these problems very quickly. Okay. I hope you enjoyed this lecture. We'll see you in the next one. Take care.